Now that your heads are probably spinning with all that information, let me see if I can make it make sense by putting some concrete numbers to the problem. In this situation, we have something that could occur here at Neumont Valley High School. We have Millvale High School who took a national test, something like an ACT, SAT, that type of thing. And on this particular national test, the population mean for all people who take it is 50 with a standard deviation of 10. The 900 students at Millvale High School who took it had a sample mean of 51.1 and a standard deviation of 10. So it appears that the Millvale students did better than the national average. And that's our question. Did they really do better, or was it just a fluke of the testing, and if we sampled them again, we might get different results closer to the actual national mean of 50. So we're going to go through the actual steps of the hypothesis test. The first one is to define the parameter. The parameter is what the information you need to know, which in this case is the student test scores. We then have to decide what is our null hypothesis, the HO, and our alternative hypothesis, the HA. Okay, we need to say, do we think the students did better, did worse, did the same? So I always think it's easier to do the alternative first. What do we think actually happened? Well, we think the Millvale students scored higher. So we're going to say we think their mean was actually greater than the national average of 50. Okay, the null hypothesis, because that's what we're trying to disprove, always has to be set to equal an exact number. So therefore, we're saying we think they actually, their mean of 51.1 was statistically the same as having a mean of 50. If we kept sampling them, we would get different results, and they would all, in the end up near 50. In reality, we could be saying we actually think their mean was 50 or less. So sometimes you will see them tag an extra little symbol in parentheses out to the side. That is not necessary if you do not wish to do it. Okay, the criteria, what are we basing this study on? Well, in our case, there's only one. We only know one distribution to use, and that's the normal distribution. So our criteria is normal. There are other distributions, such as a binomial distribution among some. And then the biggie, the other criteria, is how significant do we want this answer to be? How confident do we want this to be true? Well, rather than saying I want it to be 95% confident, I set a p-value, which is the probability. I want it, if I want to be 95% or higher that the alternative is true, that means I want the null's chance to be at 5% or less. So I am setting my p-value to be less than 5%, which means I'm aiming to be at least 95% confident that the alternative is true. Okay, on step 4, it's just where you kind of gather your data. It's sort of like where you, on the scientific method, when you write down all the results of what you're getting when you actually do the experiment. In our case, we need to write several things down. N would be how many people we sampled. Well, that was 900. This must be a big school. Their mean at that school was 51.1. The sample standard deviation for the school was 10, and then we will have to calculate the actual standard error of the mean, or the standard error of the sampling distribution by its original term, which is standard deviation divided by the square root of the number we sampled. Well, in our case, standard deviation was 10 in both instances, and we sampled 900 people. So if you divide that out, you will get 0.333, so right at 1/3. And once again, on standard error, we carry 3 decimals. Okay, then last but not least, the kicker, the one that you really need, is what is the test statistics, the z-star. What is the z-score we're going to use to look this up in our table? And basically what we need to do is we need to compare the sample mean to the population mean, which is 51.1, minus the population mean was 50, and our standard error was the 0.333. If you actually put that in a calculator and divide it, you will discover you get then a z-score of 3.3. Well, I don't know about you all, but a z-score of 3.3, that's very close, if not at the end of the chart. Okay. Finally then, on step 5, if you check back here, step 5 was actually find the probability. So use your charts, figure out what's the probability. Now in our case, we're thinking these students scored higher than that, so we are wanting, on the normal curve, we are wanting to know this very far extreme end because we think they scored higher. We are out here. So I'm going to go to my chart, look up a z-score of 3.3, and discover that, yes, indeed, that's very, very, very near the end of the chart. At 3.3, if you go over to column C, you're going to find out that the probability is 0.0005. So did our p-value we calculated, is it less than 0.05, the standard we set at the beginning? And yes, it's a great deal less than that. So since our probability is less than 0.05, then that means we have found that the null hypothesis is incorrect. And so we have discovered that our students did do better. So we would say that we would reject the null hypothesis because it came out less than what we said. We reject the null, which means the alternative is true. The MHS students did do better. Okay, I have a similar example though here. I added as an extra one year, and I'm just going to talk my way through this one. All the work's already on here. But just so you get an idea here that you can't use the numbers as determining factors. This is based on the same problem, but this time we had 25 math students who took a critical thinking test, and these 25 math students got a 54.2 with a standard deviation of 10. The mean of the entire student body is 51.1, so it looks like the math students did significantly better. That's quite a bit of difference. So the question was the higher mean score of the math students statistically significant? Did they really do better? And we were supposed to use p at less than 0.03, so less than 3%, meaning we want to be at least 97% confident that this is correct. So if you go through our steps, the parameter is what we are trying to study. What information do we need? What's the numerical data you need in the study? And that will be the scores from the test of critical thinking. And then the one that's the most crucial of all is naming the null and the alternative. And so in this case, since the actual mean of the population was 51.1, we're working off the population mean. We think our students did better, so the alternative, HA, we think they should have been greater than 51.1. So therefore, the null hypothesis has to be equal to, or less than or equal to, technically, to 51.1. Our test criteria, we're doing a normal distribution, and they told us the probability has to be less than 3%. Okay. Then the sample evidence is simply the facts they gave you. List the stuff you know. They told you you'd sampled 25 people, that's N. The mean score, that should be X bar there, is the sample mean was 54.2. The population mean was 51.1. The standard error was calculated by taking the standard deviation of 10 and dividing by the square root of the number of people sampled, which was 25. 10 divided by 5 gives us a standard error of 2. Then the most important stat of all, our z star, our what we call our test statistic. You subtract the two means, find the difference in the means, and divide by the standard error, which was 2. And so we get a z-score of 1.55. Now, once again, we're thinking these students scored higher, so if you draw out your normal curve, we are thinking that they were on the very top portion. They were on the high end of this curve. So that's what we are going to try to test for. Since we know our z-score, we know our z-score is 1.55. We simply need to go to our table and look up, once again, a z-score of 1.55. Go to column C, and you're going to be looking for this value. Going over to column C, you'll discover that you get 0.0606. So our probability that this happens is about 6%. Okay, is that less than the level they set for us? They said we had to have a probability less than 0.03 or less than 3%. We are above that. Consequently, we did not meet the requirement, and therefore, you'll see it says P does not satisfy the probability that's less than 0.03. So we have failed to reject the null hypothesis, meaning we have not disproved it. So therefore, the math student scores were not statistically significantly higher than the regular student scores. Now, you may have noticed, and that's one of the problems with this type of hypothesis testing. Yes, we needed, and that's why they really emphasize that you set that probability level in advance. We wanted it less than 3%, or in other words, we wanted to be 97% confident. You know, if I had set this one at only 90% confident, this would have satisfied it. And some people want to play that game. They want to set their level of confidence after they see the results. That's not how statistics should work. Okay, one last problem here. I want to do what's called a two-tailed test. So far, you've only done a one-tailed test. A one-tailed test, we only colored in one end of our normal curve. On a two-tailed test, as you'll see up here at the top, I actually want to find the probability it could be on both ends. So that's the difference in what we're searching for here. In this particular situation, we have the Kelly Employment Agency. They give a test. They find people, employees, and they give a test to test their skills. And on their particular test, the mean is 82 with a standard deviation of 8. Well, a new agency has popped up in town, the Brown Agency, and they claim that their test gives the exact same results. So when they sampled 36 people, their test resulted in a mean score of 79 and a standard deviation of 8. But they're claiming that a mean of 79 on their test would be the same as an 82 on the other company's test. Well, businesses in the area want to know if that's really true, so they've asked for a statistical test. So what's our parameter? What are we looking for? What's the data we need? Well, we need their test scores. Okay, now, what's our null and our alternative? Well, we're working for the Brown Agency, so we believe that the Brown Agency's test gives the same result as an 82 on the employment agency. You always use the original population data, so we actually believe our test is the same thing as an 82. Consequently, the null hypothesis has to be that our test is not the same as an 82. Now, it's not saying it has to be higher or lower, so since it could be either way, higher or lower, we say it does not equal 82, meaning it could be on either side. And that's why this is a two-tailed test. If you have an equals and it does not equal, then you're going to be doing both ends of your normal curve. The criteria then, of course, what kind of a distribution are we using? That's normal. And we need to set a probability level. Normally I'd ask you guys to set it, but since I can't hear you, we're going to set it at 0.05. So we want it to be less than 5%, or in other words, we're trying to be 95% confident or higher. Okay, we need to list all our sample data. So if we list our sample data, N, the number of people we sampled was 36. We need the sample mean, which was 79, and the standard deviation on that sample, which was 8. We then also need the population information up there as well, so we would need to know, or actually we have it up there, we know the mean, original mean was 82 and the standard deviation was 8. The two new things you do need to calculate are standard error, so we have to do the standard deviation, which was 8, over the square root of how many we sampled, which was 36. That will come out to be 1.333. The other thing we need, most critical of all, is the z-star, our test statistic, which has to compare the sample mean minus the population mean, so 79 minus 82, divided by our standard error. And if we actually divide that out, we will find that we get 2.25. It actually technically comes out negative 2.25, but in this case, since we're doing a two-tailed test, it's both positive and negative 2.25. So now we need to go to our table, find 2.25 in the Z column. Our picture is once again column C. If you haven't just figured it out, you're going to do column C pretty much all the time on these. And you're going to discover that it is 0.0122, but it would be that on both ends because we could error on either side here. The mean on the Brown test could be too high or too low. And yes, then, this makes it harder to prove because you're going to double that p-value that you get. And so if I actually add those two together, I'm going to get 0.244 as my actual probability. Okay, did this meet our criteria of less than 0.05? It did. So the good news is then that we have gotten what we expected. We're going to reject the null hypothesis, which means we have proved our alternative to be true. In this case, the Brown agency wanted the means on the test to be the same, and they are. So taking one test is not going to be better than another test. You're going to get the same results. So the Kelly agency better watch out because now they have competition. Okay. This takes some practice. There's a lot of terminology in this. Many of your problems to start with are baby stepping you into this. You don't start out doing these full-blown problems. They have you do little tiny pieces of it so that you can have a better chance to make some of the connections. Okay, you also should realize that next class is review day, so journals are due. Hopefully you should have your data collected by Friday. Work hard for the rest of the hour. If you have questions, you know where to find me. Good luck.